Hello everyone. As we all know that we are learning and understanding how to compute the space and time complexity. So today we will see lecture number 15, where we will see how we can analyze insertion sort algorithm. This is the algorithm for insertion sort. Please have a close look of it, where A would represent the array and rest of the variables, where we need two variables I and j in order to sort the list either in the ascending or in the descending order. Okay, so let us take a small example. Uh, as I gave a simple example over here, we can be given any sequence of numbers, and we are supposed to sort the list either in the ascending order or in the descending order. Depends on the question which we would be asking. So, after applying insertion sort, as I showed you the algorithm over this list, if we will, apply the above sorting algorithm, we are going to get the list that will be sorted. And sorted list will be like this: 0, 1, 2, 3, then 5, then 6, then 7, then 8, and then 9. So let we first see how our insertion sort works. So this is a small example. We how it works basically. We take 6. We start with the second element of the list, okay, and compare it with 9, and check whether 6 is greater or lesser than 9, the first element. If 6 is lesser than the first element, then we swap the two elements, okay. Then we move ahead and we take 5, and we compare this element with the first two elements of the array. If this element is lesser than the two elements, then we swap the three elements, and so on. And finally we sort the whole list of elements. So what actually we do is we put the ith variable as the first variable, first index of the array, and this would represent the jth variable of the array. As I told you that we have to take start from the jth variable as shown over here. We started our loop from j is equal to a to the a dot length means the length of the array. Then we check that key is equal to a of j. Whichever element is present at that point of time, we put that it in a variable called as key. Insert a of j into the sorted sequence. If it is lesser or greater, then we sort them. If 1 to j, then I is equal to j minus 1, and so on. We keep on doing this till the whole list would get sorted. Now what we do is, now this j is moving from the sec 2, okay, if this is first index, 2, 3, 4, 5, 6, 7, 8, and 9, and this will be a. As now this j is moving from the second index of the array to the nth slowly. When j is at some point, we are going to compare with all the elements with the list. The comparison is going to stop when we are going to find the correct location. Okay, that means this j will be taken, this element we have to take and compare it with 9. If j is the element at j is less than the first element, then we swap the elements, and after swapping, this j will get incremented and this I will get decremented. Then again this 5 is compared with the ith element, then I will be incremented with this element, and so on. So when we are going to find the correct position, now how can we analyze this? Now, you know, in worst cases, let us see how many comparisons and movements are required over here. Over this list, if j is equal to 2, which means if I am examining the second element, that what happens? Then what happens? I have to compare it with the first element. So I have to do one comparison. If I have to take this element, how many comparisons I am doing? I am only doing one comparison. If this element is, obviously if I am talking about the worst case में क्या होगा? If the element is in the descending, list is in the descending order, I have to sort it in the ascending order. The case is like that. This element, the second element, has to get compared once with the first element, and obviously this element would be lesser than this, so I have to do one movement. Similarly, when j would be incremented, j would be equal to 3. How many comparisons we have to do? Two comparisons. We have to compare this 5 with two elements. Obviously this element would be lesser than these two elements. That means we not only have to compare it twice, but we have to perform two movements as well, and so on. When j will be equal to 4, how many comparisons we have to do? This is, I am talking about the worst case. So what I am saying is, when j is equal to 2, say comparisons and movements, how many comparisons I have to perform? One comparisons. And how many swap movements? Two. Similarly, when I would increment j will be equal to 3, I have to perform two comparisons and two swap movements. When j will be equal to 4, 3 comparisons, 3 movements, and so on. When j will be equal to n, I have to perform n minus 1 comparisons plus n minus 1 moments, isn't it? So we can say, or put it like this, so we can say over here the total will be 2 times 1. 2 times 1 means 1 comparison, 1 movement. If we have to generalize this, 2 times 2, 2 times 3, and similarly 2 times n minus 1, isn't it? So if I will put it like this, when j is equal to 2, 4, 3, 4, 5, 6 up to n, j, the list, I have to perform, when j is equal to 2, I have to perform two things, one comparison, one movement. Similarly, 2 times 2, 2 times 3, 2 times 4, 2 times 5, and so on, 2 times n minus 1, the last element. Okay, so this is the number of comparisons and movements we have to perform, and this is nothing but this is a form of arithmetic progression series. This is a form of arithmetic progression series. So we can apply the formula. Out of all this, we can put 2 as a common, then we can have 1 plus 2 plus 3 and so on up to n, which is equal to, this is the summation of first n natural numbers, which is equal to n minus 1 divided by 2 into n into n minus 1 divided by 2. Okay, and अपना इसका 2, ये 2 और ये 2 कैंसिल हो जाएगा. This is n square minus n. So these are the total number required in order to sort any given list when we talk about the insertion sort. So whenever we talk about the time complexities, we don't, out of these two, the dominating term is n square. So we can say the worst case time complexity of insertion sort on n input size is equal to big O of n ka square. So in worst case, the time complexity required in order to solve this question is big O of n square. Usually worst case happens when the list is in the reverse order, as I told you, when the list is in the reverse order, like if your list is in the ascending order and you have to sort it in the descending order, or vice versa. Now the question is, what is the best case for the for the insertion sort? The best case efficiency of insertion sort is when we will have the list in sorted order as already. like I have the list like 1 2 3 4 5, and I want to sort it in the ascending order. This is already a sorted list. That means in this case we only have to perform the comparisons, but there will be no swapping movements. That means when j will be equal to 2, there will be only one comparison and there will be no movement. When j will be equal to 3, there will be two comparisons but no movement. When j will be equal to 4, three comparisons but no movement. And similarly at n, there will be n minus 1 comparison but there will be no movement. Movement means you don't have to swap the elements. So we can say the best case complexity of insertion sort is, so best case time complexity of insertion sort on n input size will be omega of n. Why omega of n? Because here I talked about the best case time complexity, and that is represented with n. This is the least time we take in order to sort the list, or in order to sort the list of elements using the insertion sort technique. Okay. And there is no, you cannot execute this insertion sort algorithm with anything less than big O of n or big O of n. What about the space complexity? We need three variables apart from the array, as we see over here. We need three variables only. We need a j, we need an I, and we need a key, right? Therefore we can say the space complexity, therefore the space complexity of insertion sort is big O of 1, that is a constant amount of time. Whatever input size we are using or having, we don't need any extra variable or space, isn't it? If our input is equal to, if our n is equal to 10 or our n is equal to 1000, these are the only three variables which we need, right? Such an algorithm is also called as in-place algorithms, when we don't need any extra variable or any extra data structure for spacing, okay, in order to store this program in the memory. Such algorithms is called as the in-place algorithm. Thank you so much. This was how we can analyze the insertion sort. Please take an example by yourself and go through this algorithm and see how it actually happens, how j moves from the second index to the nth index, how I gets changed, how many comparisons we do. This is your data structure. You must have already done this, but this is how we can analyze this. And take any example and solve this and check whether we can perform. This is the worst case. We know we are generalizing it. Sometimes we can have a list where we maybe for five elements we have to perform the comparisons and movements, and from 6 to 7 or 8 elements we only have to compare, but we there is no need for the swapping movements. So this all depends on that as well. So this was all for today, and for the assignment I will share that separately. Thank you. Have a nice day.